What's up, guys? How are you doing? You all are welcome to another session of analysis with Chi. From the previous lesson, we saw how loads could be classified according to how they act on structures, which are also called structural loads. But in this lesson, we're going to talk about classification of loads according to shear force diagrams and bending moments diagram. They're classified into two. We have the point load, which is also called the concentrated load. We also have the distributed loads. I'm going to talk about each of them and make you understand what they mean. Now we're going to start with the point loads. When we talk about point loads, I'm going to use a free body diagram to illustrate what a point load is. Looking at this diagram, it is a beam with two supports, A and B, and a load, say P, which is usually denoted with P. Now you can see that this load is acting at a point on the beam which has a span L. It's a load which acts at a point over a very small distance on a supporting structure. It is usually denoted by the letter P with its symbol arrow facing downwards. So this is what a point load is. Another example used to explain what a point load is hitting a nail with a hammer into, let's say, a wood or a beam. You would see that the nail is being hit into a particular point. That's what we mean by point load. Moving on to distributed loads. Unlike point loads, distributed loads act over a measurable length of members. It is divided into two. We have the uniformly distributed load and the uniformly varying load. I'm going to use also a free body diagram to explain what a distributed load is. Now also, this is a beam of support AB and length or span L with distributed loads along the span. It is usually measured per unit length and it is noted as W. So this is what a uniformly distributed load looks like. Another thing to note when it comes to calculations for UDL is it cannot be used to calculate or to solve a particular problem in this form. It has to first be converted to a point load before it can be used to solve. Now, converting it to a point load is simply multiplying the intensity of the UDL by its length or span. Mathematically, the intensity, which is W, times the span, which is L. So I have WL as the point load. This point load is going to be located at the centroid of the beam, which is simply the middle of the span for a rectangular beam, which is L over 2, L over 2. Converting into a point load, what I'll have is going to be like this. WL, then I'll have here L over 2 and L over 2. Now we can work with this one. So that is all for a UDL. When we talk about a UVL, which is uniformly varying load, like a UDL, it is spread over a measurable length, but the difference is the UVL is spread over a measurable length with the rate of loading varying from one point to another. It's of two types. It is of triangular load and trapezoidal load. We're going to talk about both of them. So for a better understanding, I'm going to use a free body diagram to illustrate what a triangular load is. This is a triangular load diagram. This shows that it varies. We can see that it varies from one point to the other. So a triangular load is a load which magnitude is at 0 at one end, which is at this end of the span, and increases constantly towards the other end of the span. So which is why this is our W, which is Newton per meter. This is our span, which is L. Now also, as I said earlier, you have to convert it to a point load to be able to solve with it. For a triangular load, is quite different from a uniform distributed load. In this case, we're using the shape of the triangle to convert it to point load. So we're going to use the area of the triangle, which is half base times height. It is seen from the diagram that the base is the length, which is also known as the span L, while the height is the unit load, W. So we have 1/2, which is half, times L times W. We'll have WL/2. Having done this, we've successfully converted this varying load into a point load. Point load is going to act as the centroid of the beam. For a triangular load with span L, the centroid is going to be 2/3 of L from its peak and 1/3 of L from its base. And then we'll have our converted point load as WL/2. So that's how to convert a triangular load to a point load. Moving on to the last but not the least, trapezoidal load. It is almost the same thing as the triangular load. The shape is going to be in the form of a trapezium, which is going to be like this. Also, the load is acting on the span length in the form of a trapezium. It's usually formed by the combination of a UDL and a triangular load. So from here, you see that this is a UDL and also it is a triangular load. You can see that this trapezium can be divided into two, which will result to a triangle and a rectangle. So the triangle is a triangular load while the rectangle is a UDL. So that is how a trapezoidal load is formed. I am also going to be showing you how to convert this load into point load in subsequent videos. So let's do a recap of what we've learned today, shall we? Firstly, we talked about point loads. It's a load acting at a point. It's usually represented by the letter P, using a nail and hammer as an example. Then we moved on to uniformly distributed load, which must be converted to a point load before use for any calculation. And converting to a point load, we achieve that by multiplying its load by the length of the span. Also, we talked about varying load, which consists of two loads, triangular load and trapezoidal load. We also talked about centroids. For a rectangular loading, the centroid is usually at the middle of the loading, which is half of the span, while for a triangular loading, it's usually 2/3 of the length from its peak and 1/3 of the length from its base. So that'll be it for today, guys. Don't forget to subscribe to my channel, like, comment, and share. Thank you. See you guys in the next video.